So there's a place for ISN page and all that. You can just ignore that. This isn't necessarily going in your ISN. But this is a square root, also called a radical. We know all that, right? If x squared equals 25, then what is x? It's like a knife through my heart, people. Come on, you know what's missing. Plus or minus. Plus or minus 5. That's huge. Okay, rule number 1 about square roots. When you introduce one, you keep papers on your table. What do people think you're doing? Are you getting new here? Come on. All right, so then square root of 26. What would x be? I'm sorry, if x squared equals 26, I just told you, but it would be, they threw me off because they're just sitting there staring at me, plus or minus square root of 26, right? We can't simplify that one. We're not getting a decimal here. We're not guessing at a decimal. We're not touching a calculator. Like sometimes that's the best you can do. All right, so sometimes, and it seems more often than not, some of you are taught, how many were taught, the first way you were taught was to find the biggest perfect square that divided into the number? Anybody? No? Okay, that's good. Because that's not a bad thing to do. It's just a bad way to start. Were y'all taught by the factor tree? Or do you not even know what you were taught? How many of you are really not even sure what the heck is? Okay. How many of you like, I really kind of have no clue what's going on? Just be honest, because, okay. All right. And so even if you kind of do, hearing it again won't hurt you. So the prime factorization here, this is like, you literally did this in elementary school when you started talking about numbers and multiplying and dividing, whatever. So I'm not even talking square roots here. If I just have the number 45, okay, just that, and I'm going to do the prime factorization of this. I find two numbers that multiply to give me 45, like 5 and 9, right? And then once you get to a prime number, hence the word prime factorization, we're going to circle it, and the end of that's the that branch. 9 is 3 and 3. Okay, so that is the prime factorization of 45. Does that make sense? It's called a factor tree, something that you do in elementary school. I don't know how long you do it and what all you do it for, but if you can do that, you can simplify any square root, and you can do things in certain ways. Hopefully, as we have this little refresher, you will get to a point where you realize you are kind of ready for the shortcuts, and some of you are already there, but you're just, again, kind of not sure what's going on here. Let's simplify. Let's take the square root of 27. You should get to a point where when you look at that, you know the answer. If you're not there right now, that's okay, but it comes with some practice. So we're going to work this two different ways. We're going to work this with prime factorization, right? Just like we just did. So what are two numbers that multiply to give me 27? 9 and 3. So 9 and 3. 3 is a prime number. Then 9 is 3 and 3. Once you have finished all of your branches, right? When you take the square root of a number, you're looking for a number times itself that will give you that number. So when they come out of the square root, they can only come out in pairs. So we look for pairs. Well, I have 2 3s, and they don't have to be right next to each other. That comes out as just one plain old 3. This guy is alone. There's safety in numbers, so he doesn't get to come out of the house, and it's 3 square root of 3. That is the simplified version. Okay, does that make sense? Ooh. I don't know. I haven't heard the birthday cake one. Okay, I'll have to ask her. Birthday cake, yeah, and she talks about glue and things. Like, I need to go sit in her class for a few days. Okay, maybe. Can anybody explain the birthday cake? Because I'm not sure. And the prime numbers are on the left. So it's kind of like this. You're just going maybe vertically and doing it a little bit different. So yeah. And again, I am not saying you have to do it this way. If you do it the birthday cake way, whatever that means, I'll make sure I figure that out. And it works for you, that's fine. Okay? So part number 2 to this is that when you start off, so we're going to start with just the same square root of 27. When you get to this first step, right, and you have circled a prime number, when you have something that's not a prime number that's a perfect square, you don't have to go any farther, because you might get a perfect square like 16, which is going to have a whole lot of 2's come out of it, right? And you don't want to go on. Once you have the perfect square, you can stop. Whatever is circled, you would look for pairs. This one doesn't have one, so he stays underneath. And then I can just go ahead and take the square root of that, and it comes out. Does that make sense? That's where you start. Or you can sit there and think, what is the biggest perfect square? But sometimes that's going to take you longer than just starting it. If it's not a number that you just recognize factors of in your head, at least start it and start writing some stuff down so you can get to where you need to be. Okay? Does that make sense? Does that help? All right. So let's go, let's see, so that you have more room. Let's go ahead and go flip the page over. Let's go to right here. Because I'm going to give you the square root of 336. When you have large square roots, okay, do you just know the factors of 336? I'm guessing most of you probably don't. I don't either. I'll be real honest. I have no idea. And I could sit there and I could guess and check for perfect squares, but that is a complete waste of your time. This is an even number, so what do you know it's divisible by? 2. Okay. So then, if I look at this, is this number also divisible by 3? Yes. How do you know that by looking at it? You add up the digits. 6 plus 3 plus 3 is what? 12, and that's divisible by 3. So, if it's divisible by 2 and by 3, what's it divisible by? What's 2 times 3? 6. So I know it's divisible by 6, or you could do 2 and then you could do 3. It doesn't matter. And then, how many times does 6 go into 336? How many times does 6 go into this number? Like, this would be 6 times what, basically? Okay, do you see how starting with a bigger number makes it harder, right? Okay, so we're not going to use 6. Let's go ahead and use 3 instead. Can I divide 3 pretty easily? Yeah, what is it? 112. You see how that was a little bit easier? I just changed which number it was to make it easier on my brain. Not a problem. Now, this is a prime number, so I'm going to circle it. Is 112 divisible by 3? No. But it's, well, it isn't, because 2 plus 1 plus 1 is 4, right? And so it's not divisible by 3, but it's even, so what is it divisible by? 2. So this is going to be 2 and what? 56, right? Because half of 100 is 50. Right, so 2 and 56. You with me on that? So then 56, not a prime number. What are 2 numbers to multiply to give me 56? 7 and 8. Like, I could still, if you weren't sure, you could still keep going by 2s for a while, right? But 7 and 8 work. So 7 is a prime number. I'm going to circle that. Then 8, I can break that into 2 and 4. And then I'm going to break 4 into 2 and 2. Okay? Now, 4 was a perfect square. I could have stopped there, but I want you to see what's happening with it. Everybody with me on all that? Okay. So now I have all my branches are done. I start looking for pairs. So how many, do I have another 3 besides this one? No. So he's going to have to stay inside. Do I have another 2 besides this one? Yes. This 2 I can take out with that 2. So it comes out as what? 2. And then the 7, does he have anybody? No. So he has to stay inside also, and everything's multiplication. And then does this 2 have another 2 to go with? Yes. So that comes out as a 2 also, and everything gets multiplied. So what I end up with then is 4 times the square root of 21. Okay? Now, let me show you a different way you could look at this. If you wanted to sit there and you wanted to think, okay, what's the biggest perfect square that divides in there? I mean, you can do that, and what would happen is you would get the square root of 336, and that's going to be 16 times 21. But think about all the math you would have had to do to figure that much out, right? And at that point, then you can go, oh, this is a perfect square, so all I have to do is take the 4 out, and then this is 7 times 3, and they don't have any pairs, so it stays the square root of 21. So that might look easy. Oh, that's much easier. Well, yeah, if you know 16 divides into it, right? And if you don't know that, then you just going through the tree, you're probably going to be done, or the birthday cake, whatever. You're probably going to be done a whole lot faster than if you just did it. Okay? We're good? Any questions on that? All right. Do you know what to do when there is a number on the outside? Do you know how to handle that to simplify it? Okay, you leave it, this little guy right here, he just sits and waits. He just hangs out, because he's outside already waiting for his friends to join him, right? Is there a perfect square that divides into 48? Or are you not sure? Okay, eventually you start to recognize some of that stuff. If you're not sure, that's fine. What 2 numbers that multiply to give me 48? 6 and 8. Does 4 and 12 work also? Yes, and 16 and 3. Okay, so there's nothing wrong with any of those that you said. I'm going to use 4 and 12 just for a reason here. So this guy's going to just sit and wait, and I'm going to work on this 48. So I'm going to use 4 and 12. I could use 6 and 8. I could use 16 and 3, because 16 and 3 is going to get me there quicker. But you're not always going to recognize that, and that's okay. But I got 4 and 12. Well, 4 is a perfect square, so I'm going to leave them alone. I'm not going to split them up anymore. 12, I could do 2 and 6, or I could do 4 and 3, right? 3 is a perfect square. Now, the fact that 4 is a perfect square means I could just take the square root of it and take a 2 out and take a 2 out. But even though these aren't primes, they're still a pair, right? So since I have this pair of numbers, these 2 just come out as a 4, and this 3 can stay underneath. Then this guy, he comes down and joins them, and that's where we get 16 square root of 3. Since this isn't brand new information to you, you learning how to do it more efficiently is what's going to help you. I mean, if you have no clue what's going on, then I would suggest the entire tree for a while. Hopefully, or the birthday cake, whatever. But you can, I mean, I got to figure out what that is, so I'm saying all that stuff right to you. But you can take shortcuts in that as well. But if shortcuts are messing you up, do the tree. But learn how to just see it. And again, this is 16 times 3. Oh, that's a 13. 16 times 3, so that would just be 4 square root of 3. The 3 stays inside. And don't get them mixed up, which is on the inside and which is on the outside. Any questions at this point? All right, good deal. So, when multiply, I didn't even fix my mistakes that I had on here. Multiplying radicals, you can multiply everything inside the radicals together and everything outside the radicals together, but they do not get along well. You cannot mix and match, all right? So we are going to do a few different examples of what can come up and how you handle this multiplying of them, because we got to be able to simplify them. We also have to be able to multiply them. So if I have the square root of 2 times the square root of 6, right? What is that going to become? Square root of 12, right? And then I got to see if I could I simplify either one of these before I started? No, right? I mean, this is just 2. I can't do that. That's 2 times 3. Nothing comes out. Can I simplify this one? Yes. What are 2 numbers multiplied to give me 12? 4 and 3. So if this gives me 4 and 3, this is a perfect square. I take the square root of that, and I get 2 square root of 3. To check yourself, as long as you don't have something out front, because you can't check it here, but if you're just simplifying a square root, you take what's on the outside and square it, multiply what's on the inside, you should get that back. So 2 squared is 4 times 3 is 12. Okay, we all good with that? All right, and then what if I have square root of 5 times the square root of 5? What does that equal? 5. Okay, because what's happening, but I don't want you actually doing, is the square root of 5 times the square root of 5 is the square root of 25, right? And then that is 5. Does that make sense to you? I didn't put my little signs back up, but in geometry all year I have square root of a monkey times the square root of a monkey is a monkey, because it drives me nuts. This is super easy and it's going to come up a lot, so don't mess it up. Square root of anything times itself is just whatever's underneath. Square root of a million times the square root of a million is a million. I mean, you don't have to actually do any math there. Okay, we good? All right, so number 3, let's see, we're going to do this one. I'm going to do 2 square root of 3 times 4 square root of 5. Can I simplify anything before I start? No, because if you can simplify before you start, it will simplify things. That's why it's called that. What is this going to give me? 8 times the square root of 15. Because you can multiply everything outside together, everything inside together. Then we got to check and see if we can simplify this. Can I simplify this? No, because this is 5 times 3, and there's no pairs, so they both stay underneath, and that's it. Everybody okay with that? So what if I have 3 times the square root of 7 squared? It's what? There's a power of a product rule that says that this is 3 squared times the square root of 7 squared. What's 3 squared? 9. What's the square root of 7 squared? 7. So the answer is 63. This is the same thing as 3 times the square root of 7 times 3 times the square root of 7, right? So 3 times 3 is 9 times 7, you get the 63. This type of thing comes up a lot too, and it's missed a lot. You type that in on your calculator, you're most likely going to type it in wrong. 99% of people do, okay? Which means it's going to give you the wrong answer, and your calculator is going to give you 21, and you're going to be like, oh, it must be right because it came from the calculator. And no, you're totally wrong because you're trusting something that's wrong, okay? It's only as correct as what you type in. All right, next part. So that's multiplying. When adding and subtracting radicals, always treat them like variables. Right? You treat them like variables because remember, we don't get to mix and match much. So if I have something that is 2 square root of 3 plus 3 square root of 5 plus 4 square root of 3, I may be able to combine some terms, I may not be able to, but this is combining like terms, just like you would if they're variables. So this is like 2x plus y plus 4x. These have the same square roots on them, right? So when I add those two together, that gives me what? 6. It's like, in literally, these are the same types of things y'all do in kindergarten, and you don't even realize it's the same. This is like 2 teddy bears plus 3 fish plus 4 teddy bears. So I have 6 teddy bears, and I still just have 3 fish, right? You see how that's the same thing? They're things. You think of them as things like variables or tangible items. We good? That's the best I can do. I don't get to add what's underneath, nothing like that. Okay? Everybody okay with all that? All right, grab that second piece of paper. I'm going to talk about rationalizing here in just a minute. Okay, so I like this thing because it's kind of a concise, everything all together here. Not necessarily going to read all the words to you, but they will be important to you if you had to go back and you were trying to figure out what to do. So this is kind of all-encompassing from the different things that can show up. So if you have something that looks like this, then this is explaining to you what to do, which is basically what I'm going to say to you also. Now, on this one, we could do the tree, 100%. There's not a whole lot of room, so we're not going to. But do you know what a perfect square is that divides into 32? 16. Okay, 4 is also, but it's not the biggest perfect square. So sometimes when you don't pull out the biggest one, it's simplified, just not simplified all the way. But even if you started with 4, you could do the tree and figure it all out. But this is 16 times 2, right? That's my prime number. This is a perfect square. I take the square root of that, and it's 4. 2 stays underneath. Square root of 2. Okay. Everybody okay with that? And if you need to, the tree stuff is on the other page if you needed that. All right, so then if you have something like this, so we could just multiply them and then try and simplify, but that gives you bigger numbers. You always want to try and simplify first. This right here isn't going to simplify because that's just 2 times 11, and they both have to stay underneath there, right? But this is 4 and 2. This actually simplifies to the square root of 22 times what? What does this become? The 4 comes out, it is 2 square root of 2. Okay. So then, we can multiply these two together, but look at what's happening also. I can split this one up. I can split this up into the square root of 11 times the square root of 2 times 2 times the square root of 2. Just like any other multiplication, if you think about how things are built, it's going to help you out some. So when I get to this point, this whole number 2 is just this. What's the square root of 2 times the square root of 2? 2. And then the square root of 11 is still just the square root of 11. And I get 4 square root of 11. Everybody good with all that? All right, so when you have exponents underneath, if they're even exponents, they're perfect squares. So all you have to do is divide these by 2 and the exponents by 2 and take them out. Because basically this is the same thing as a squared times a squared. Would you agree with that? And this is b to the 4th times b to the 4th, right? And you wouldn't have to write that when you're doing it, but that's what's happening. And so one of them comes out, and you just have the square root of, I'm not square root anymore, sorry, dang it. You have a squared times b to the 4th. That's your answer. If they're odd, you have to take one of them off first. So I would have to make this into the square root of like x squared times x, and then y to the 6th times y. And I'm not saying you would necessarily have to write that, but you at least need to be thinking about the fact that one's going to have to stay behind because they're odd. Then you take the leftover and divide it by 2. So 2 divided by 2 is 1. So this would give me x on the outside. 6 divided by 2 is 3. And then you're left with x times y inside there. And that is as simplified as we can get. All right, so now fractions and rationalizing the denominators, because this is what we're about to have to use a lot of. And this, for sure, you had to rationalize the denominator in geometry when you were doing special right triangles. So that should have been done with you for sure. But when you have the fraction under a square root, you can, if you can take the square root of the whole fraction, which most of you don't really think that way, I mean, you could do it that way. This one isn't going to work like that anyway. I would split them up into 2. This is the square root of 17 over the square root of 144. Okay? Can I do anything with the square root of 17? No, that's a prime number, so the square root of 17 is the square root of 17. What's the square root of 144? 12. And then I can't do anything else with it. All right? It is fine to have a fraction with a square root. It is not okay to have a fraction in the denominator. A square root in the denominator. Now, if you can reduce the fraction before you move forward, reduce the fraction. So this is 15 over 5, right? And that's 3, so that's just the square root of 3, and I can't do anything else with that. That's it. If it's split up, you can put it back together. So this 24, square root of 24 over the square root of 8 is the same thing as the square root of 24 over 8. Can I reduce that? What does that give me? What's 24 divided by 8? 3, so it's the square root of 3 again. And I didn't have to do anything crazy with my square roots. Okay? Everybody okay with all that? All right, so now the rationalizing part. It says make sure there is no radical in the denominator. By rationalizing the denominator, that sounds all crazy hard, but that just means we're making it rational because currently it is irrational. So you decide to, I can't divide this out. Like I can't take 15 divided by 3. That doesn't work because these live in 2 different worlds, right? The square root in the denominator is what is illegal right now. So I take this, and whatever the square root is, that's what I'm going to multiply by. You can multiply anything by a value of 1 and not change its value because we can't change the value, right? So I'm going to multiply by a fraction of 1, which means the numerator and the denominator have to be the same. This is what determines what it is. So this is the square root of 3 over the square root of 3. Then multiplying fractions is easy. You just multiply straight across, and we're going to get 15 square root of 3 over what? 3. That's like the whole reason I did it, right? Now my square root's gone in the denominator. Then you reduce if you can. Sometimes you can't, and you're left with an ugly fraction. Can I cancel these 3's? No, because I treat that like a variable. It's like 15x over 3, but I can reduce this, right? And this gives me 5 square root of 3 in the end. Okay, everybody okay with all that so far? When you have it in here, if we can't reduce that, we're going to separate it just like we did on the page before. So this is going to be the square root of 4 over the square root of 5. Can I take the square root of 4? Yes, what is that? 2 over the square root of 5, which is just the square root of 5, right? Can I leave it like this? No. So I have to multiply by square root of 5 over the square root of 5. And then I just multiply straight across. And that's going to give me 2 square root of 5 over what? 5. Can I reduce that fraction at all? No. It's just an ugly fraction, and that's okay. Okay? Everybody okay with all that? All right, good deal. So now we're going to talk about adding and subtracting again, which we already talked about a little bit, but this is kind of puts it all together. So if you have like terms and we're treating them like variables, this is like 2 elephants plus 3 elephants, right? So then how many elephants would you have? 5. So together I get 5 elephants, or 5 square roots of 5. Okay. So this is like monkeys. Not okay. We can magically make a giraffe into a monkey though, right? Because I can simplify this. Bet you didn't know you could do that. So when I take the square root of 8, what is this going to simplify to? 2 square root of 2, this is 4 and 2, right? So if you're not to, hopefully you get to a point where you can just look at 8 and know that. You take the square root of 4, so this is going to give me 2 square root of 2 plus 6 square root of 2. So now I have 2 monkeys plus 6 monkeys gives me what? 8 monkeys. Right? 8 square roots of 2. Everybody okay with that? All right, so when you have something like the distributive property, you distribute just like you would no matter what it is. Multiply with that. 5 times 6 is what? 30. What's 5 times 3? 5 times 3 square root of 3? 15 square root of 3. Okay. Yeah, does that become 45 square root of 3? No. Okay. This is my answer. That's a very common wrong answer. That does not equal 45 square root of 3. So write that down just in case you're ever tempted to do that. That's a big fat no-no. That's like saying 30 plus 15x. That's it. 30 plus 15x, right? It doesn't become 45x. When you first started with variables, it probably became 45x a lot on your paper. And like, nope, doesn't make sense. All right, so then we have power of a product rule, which I know we talked about on that other piece of paper, but it's on here too, so I want you to see how this works. Power of a product means this. This is 3 squared times the square root of 2 squared. Again, not saying that you have to write these intermediate steps, but I want them on your notes so you know what's happening. So this is going to give me 9 times what? 2, which is 18. Okay? This is the same thing. Hang on, we're not done. This is the same thing as 3 square root of 2 times 3 square root of 2, which would get you there the same way, right? If I have 5 plus the square root of 7 squared, does that equal 5 squared plus 7 square root of 7 squared? Is that what would happen there? Okay. This does not equal this. These are different. Do you see how this is multiplication and this is addition? This is for the same reason that x plus 3 squared does not equal x squared plus 9, right? Have to FOIL. What this would actually give me is x squared plus 6x plus 9 once I FOILed that out. Basically, you'd have to FOIL that too. We're not going to do that right this second. Just note, don't get to distribute. I got to here because it was all multiplication. It's the power of the product rule, not the power of the sum rule. Okay, does that make sense to you? Any questions at all? Now, tell me what questions about square roots you have that I did not cover. Anything? Anything I need to re-explain to anyone? Okay. Hopefully you at least got something out of it. I don't think that all of you necessarily needed all of this, but I think everybody getting a little bit of a refresher definitely would help, because this is another one of those things that takes some practice. So if you weren't really comfortable with them, you might need to go practice on your own, or you might have been fine and felt like I wasted your time, but you know, I'm sure you learned something. Did you at least learn something or refresh on something? I hope. Okay. All right, any questions at all? So just hang on to those, do whatever you want to do to keep up with them so that you have them to refer to. If anything else comes up, let me know. All right.